Hey everybody, we're back live. Boy, I'm going to do a lot of lives today. We're going to do, if you're going to be around later on, I'm going to be doing a live tonight, my face-to-face Fridays with Dissident Science. But right now we are with my dad. Say hello, Dad.
Hello, Dad.
But we're here to talk, and we have some chicken scratching drawings that we're going to be talking about. But where are we? We are having our meeting, and this is part of it. We're also going to be talking about some other things. We also end up talking about concepts, so we try to record these for prosperity, so that when we become just so insanely famous that we have. No, that's not why. We're here to talk about our we're here to talk about our book and those interested in this model. So, anyways, let's put this up. What before we go to that, where are we again?
Okay, all right.
Wait,
Let me.
hold on. I'm going to say where we are.
Oh,
Okay. So
okay.
what we're going to do, basically where we're at is my dad's been going through the book a lot about where things go. We've had discussions on where things go. We've done some movements in that in the table of contents.
I changed that recently, by the
Yeah.
way.
And then also, the biggest thing that we really need to get done are the graphics, and that's in my area. So we need to start talking about the graphics. And this weekend, we're going to have a meeting tomorrow at some time to talk about what graphics we need and how to attack those, because I want to have sort of a way to do all the graphics, because there's lots of graphics, especially in the circuit area of the electronic circuits. So if once I get through, and in the for those people, and I know we have actually people interested in when our book is coming out. That is coming out, of course. What we're saying is fall time, but once we go through all the graphics and I get all at least one version of all the graphics, we're going to take the book and do a printout of it for just for ourselves to see how it's looking and everything, and we will be much closer at that time. So that's where we're at. And today we have some things to talk about. My dad wants to talk about in that vein. So let me know when you want to put up the graphic, because we've got graphics today.
Yeah, well, as you said, tomorrow we had planned to talk about the graphics. That's when we were going to do it. And I thought, well, since Friday night was normally a video night for the book, why don't we talk about some of them on the video, give the listeners an idea of where we're at. Plus, you'll find in this next discussion that I've been saying one of the things wrong. All my listeners have been hearing me say this. This is what I said is that's wrong. I've been saying that G1 gravity can act on the atom, level 1 atom. That is incorrect. And I've repeated that I don't know how many times. And as of my work yesterday in trying to define the figure and making sure it's right, I found out that statement's wrong, and so I want to correct that. And we're going to talk about those right now, and you can flip to my Scribble page, Dave.
Okay, all right.
You can skip over and let them see the Scribble page. There you go.
I think we can put it up with us. It doesn't
Yeah,
change
I
anything.
started that yesterday and been drawing on it all over and over the place. We're only going to talk about sort of the middle section. Yeah, right there, David. If you go down, start at the top. Are you there,
Yeah,
Dave?
yeah.
You start at the top where it says level 1, and then just below it's got two particles, N1 and G1. We're not talking about that now. That's going to be later, tomorrow probably. But just below that, I have an atom. And you'll see I have it labeled the hydrogen atom. And that hydrogen atom has one N1 particle making up the nucleus and one G1 orbital uh, replacing the electron, and hence you have, as I've been saying over and over again in the past, I've been saying it's G1 gravity, but you'll see I got it labeled. If you look at it close, I got it labeled F2 force. Not, it's not it's G2 particles, F2 force that is doing that. So why am I saying that? Well, there's a note over to the right where I say, well, gravity is what, does one thing, and gravity can cause the orbit because it's gravitational. But a G1 particle will not cause that G1 atom to orbit, a G1 particle to orbit. It will not do that. It's only a collision. That part I've stated correctly in the past. G1s only collide with G1s. So it can push it. It can push it by, the G1 particle can push it by hitting the G1 or by hitting the N1. But in effect, if you had an atom floating in space, that's all that would happen every time you had a collision between the G1 particle field, one G1 particle, and any part of that hydrogen atom. All it does is push it in some direction. That's not gravity. What you have as an orbital is a gravitation, a path that's caused by gravity, and the only thing that can do that is G2 gravity. So it requires G2 gravity to create the orbital for a level 1 atom. And that's the way I need to have Dave draw it, using his own way of doing it. Not G1, you've got to have, that's G2 gravity that is causing the G1 to orbit, because G2 works gravitationally with the G1 and it acts gravitationally with the N1 because it can pass through both. It can easily pass through. As it passes through, it can hit or scatter. In this case, get trapped seems, yeah, it could get trapped. You could have two G1s orbiting as long as the system would allow it. So that's what we need to, only thing I want to correct in the level 1 atom is that it's G2 gravity that's causing it to orbit. And collisions only push it around. So it jumps around in space.
But so you can just imagine the nucleon is the sun, the G1 particle is the Earth, and then the graviton field, which is all these small particles going very fast, is what's keeping that and going around. So you can sort of bring it down.
By the way, that G2 particle is moving we're estimating it at c squared. They're moving very fast.
Right.
So you can treat the G1 orbital as if it were stationary around the N1 nucleus, calculate the forces and calculate where it's going to go next, because that G2 particle is extremely fast. Just like the G1 particle is faster than the sun and the Earth, which I think is what you were trying to get to.
Sure.
Okay, so let's go down below that, and now we have a hydrogen gas. Two hydrogen atoms drawn together. Nothing different here. The G1 orbitals of a hydrogen gas are controlled by G2 gravity, or which I label as F2. The net force is F2. Notice you have two F2 forces pushing on the nucleus of each atom, just like the G1 pushes on the Earth and the Sun to push them together. But this time it's the F2 force pushing them together, but because it's a gas, there's something keeping it apart. What's keeping it apart? So it's a gas and doesn't become a solid. It's on I drew it on there.
Oh, you drew it.
It's on
Strong
the picture.
collisions.
You got collisions. Why do you have collisions? Because I've drawn them both going counterclockwise.
Mm-hmm.
They're both going counterclockwise.
The
So
Deneau effect.
You have a huge number of collisions in the middle, mitigating against the force pushing together. And you end up with a balance where they stay together, but they're not locked. They're sort of
But they
flexible.
probably could lock once in a while, huh?
Well, they will if you go to the right.
Okay.
That's
So you're doing what we call
the new effect.
the Deneau effect, but it's not opacity. It's what's the word for polarity?
Well,
This is
you
what
could call
polarity
it-
is about.
You can call it polarity. I'm saying that when they're opposite, figure 3, Same drawing, only difference is the orbits are opposite to each other.
Mm-hmm.
One's counterclockwise, one's clockwise. Now there are collisions, but they're not as many and not as strong. But so the F2 force is strong enough to hold it together like a solid.
That's my
I
explanation
know it
for
is.
the.
That's why I wanted you to see it.
So it's, even though I've explained this for a long time, it's like always. My dad says that's nice, but I don't. I haven't looked into it. And when I look into it, then I understand it. Then I'll say, yeah, I agree with you. That's the right attitude. Is not to believe anything your son says. I'm kidding, of course.
Yeah, because I've recognized. I told you. In fact, I made a note in our book. There's a big note, and you need to read it sometimes. There's a note in my book about
no.
that very subject when you describe that, and I say this is a neat idea. And I don't know. I wrote that 6 months ago.
Oh, so even though it's been around a long time, it was only 6 months ago that it was a neat idea, even though it was actually one of the very first ideas that I had before to even write the book. Because it was, you had come.
I'm not arguing you had the idea. I'm just,
No. It's not even arguing that I had the idea. It was just interesting that for me, though, numbers of things, the Denew effect, and the electron, the two things, the electron, photon, graviton, and particle for magnetism all being the same. Having that, then I also saw the Denew effect. I said that's exactly why, because what they do for atoms is if you look at two atoms or even H2O, we know the angle of the oxygen versus the hydrogen, and we know all kinds of things. But why are they in those places and why do they stay there? Well, we say that all the molecules have polarity, and what's polarity? It's charge from particles, and of course we know there's no such thing as charge. So how do these things work? Well, that's what I'm saying. The flows is what keeps them together or apart or repelled or get eventually into a steady state.
but you can see here like some of the things I've said in my videos is that you always have opposing forces. You always have opposing forces, whether it's a gas or a solid, they're opposing.
Mm-hmm.
The question is which force wins out and what is the condition that makes that happen? And it's David's flows that does that. It's really a neat way to see how hydrogen gas can be a gas.
We should write a book on this. Oh, we are? Okay. Here. I want to put this closer to you.
So,
I'm louder than yours.
what I really like to see in the book right now is that when I start describing, after I go through some preliminaries in the Hack 3 gravity section, you get this example because you start seeing how the two forces interplay with each other at different levels in a clear way. Here's the picture one is the F2 just giving us the G1 orbital. Then you got the two of them together with G1 orbitals, but then you've got the flows making it a gas or a solid. Let's look at number 4.
Where's it? Oh, there's numbers?
Yeah.
Oh, look, they have numbers. Oh, wait a minute. I don't see 4. Where's 4? Oh, there it is. I see 4. For those who've not seen 4, there it is.
There's 4. Well, I drew 2 copper bars. That's what I was supposed to say.
Okay.
And we would normally think that it's G1 gravity that is pushing those together. So I got F1 pushing on the center of gravity of one, pushing on the center of gravity of the other, pushing them together. However, you also have an F2 force field around each bar. And as you can see, the F2 force can push 2 atoms together. If they can push 2 atoms together, why aren't they contributing to pushing the copper bars together?
Well, then you get into the problem of infinity in our model, which ends up saying that gravity is really all the forces at all the levels pushing things together.
That's a good idea, Dave.
I've thought about this too,
Yes,
and it really is sincerely, because if you look at just the G1 gravity, well, one of the things that people do talk about is, what is gravity in their models, right? And a lot of the people are talking that the gravity is, between atoms, and of course, in the sort of the Lesage effect with G1s, it sort of is, but it isn't. And then you think of to yourself, well, how is it that then you have gravity so prevalent inside like a cave? It's almost like all the gravity's getting through. That means all the G1 particles, and then you got light. Well, why doesn't light? All kinds. You get all kinds of what's really happening with this model. And one of the things is, and this would, what do you do, and what does this mean? Is that you know gravity's much more at the atomic level than anything, and if that's the case, then how does that work with the shadowing G1 effect, G1 gravity?
Well, there's G2 gravity. There's in between those two hydrogen gas. There's a shadow effect in between those two atoms, specifically the nucleus. And the same thing that's for figure 2 and figure 3. So, you have shadowing effect at level 2.
Well, I understand that.
Okay, and that's what's happening up by the copper bars. The real question is, what percent, if you try to quantify it, what percent of the gravitational force that we measure is made up of G1 gravity versus G2 gravity?
Yeah, I mean that's a good question, and I've thought about it, but I think if you look at it I think what it is that when you have big bodies, you're talking about G1 gravity. That's the major influence between them, like the sun and the moon and
Yeah.
celestial bodies. When you're talking about atomic structure, of course, you have the G2 field, and it's just like having stars in a galaxy. Now, if you have a bar, it's like having a bunch of stars with a bunch of things going around it, orbits around it, and then you have the gravity at G2 level pushing those together. So it's part of our model, which is infinite part of it, which I believe is totally true. But I think we're still not getting a super grasp, even ourselves, on what that relationship is and where it's affecting more.
We don't know that percentage I was asking about, but the fact that the readers, by going through 1, 2, 3, and 4, I'm hoping to make a very clear statement that you can't actually, at least on smaller objects, you can't just say it's G1 gravity. You have to they have to both be accounted for.
Well, as you get closer and you get smaller, you're getting closer to that world, and you're shrinking yourself down and looking at the smaller, what Borker calls unicosms. If your unicosm is at our level and the atoms, you don't see atoms, we're looking at G1 gravity, really, the effect of that. If we go down to a unicosm that's below that, now we're down a level or more or less, then we have to say, oh, well, what's really affecting more this level? I think oh man, this is fun. I think what we could say is that gravity basically moves things together. The G1 moves the group of G2 gravity things together. So that's the way I would look at it. So you have a bar, and it's the G2 gravity that's keeping this bar together.
So
Then the whole bar,
G2 gravity around some of the atoms right there.
And then the bar itself, as to what they do and that whole group of atoms, is really, that's what affects those groups, and the movement of the groups are G1. That's the answer. I answered it. Okay, Dad, that's it. You didn't, so don't know, and I answered. I'm really the person doing all of it. He's just a pretty face.
Wait a minute.
No.
You know what? I throw the ball up and he uses a tennis racket and whacks it. He had one out here just this morning.
Yeah, it was for bugs. For our daughter trying to zap bugs. But no, I mean, I think it's really interesting. It's one of the things with the model. But again, what's surprising is now I have a visualization of it. I think that would be a wonderful graphic because basically what you have are groups of atoms. So at the atomic level, you have atomic level F2 force, the gravity 2 force, are keeping that mass together. And then, but if you have two of those masses and they're separated by quite a distance at the G2 level, those masses and their movements aren't affected really too much by G2. The G1 is going to have more of an effect on that. And if you think about it, that's the way the whole universe works. Then, I mean, it just sort of, it's interesting to see in my case how our model sort of gives me a new visualization of how things were really working.
You're welcome. Oh, that's a collaboration, by the way. We're working together on it because he was the one pushing the
new effect.
The new effect at the atomic level, and he's right. I didn't buy it right away.
When did you buy it?
When I wrote that note in the book.
Oh,
Whenever
which one?
But
how long ago was
that? Go
that?
into history and look.
But I mean, was it like recently, or was it?
Oh, I don't know, several months ago.
Okay. All right, I have no problem if it takes him time. It means he's thought about it well.
But you get my point. If we go in the book with that sequence, it really, I think it gives a real good, for somebody who, you have to read it, you got to look at it, think about it to get it. But I finally got it right. In those pictures, I will not say that the G1 is gravitationally pushing the atom. And I've said that so many times, and that's wrong.
Well, I know that's wrong. I'm not. I guess what I didn't hear, I just didn't hear it because I don't think he would have said something like
that. Yeah, just try. Keep trying, Dave.
Right. Okay. So all right. So that's pretty good. I mean, we've gone 22 minutes already.
Yeah, well, you see, there's enough work there for you to get started on.
What's level 2 here?
Well, because I'm going to go on to level 2. Now, there, see, you got the G3 particle.
Oh, man. Oh, this is interesting. I'm going to have to change the title to the G3 as well in here. Look at this.
No, I talk about it, but I duck very fast.
Yeah, so I see you have a question mark here.
Yes. But if you go up further to the top where we ignored it, you'll see that right there I was struggling with
Where's right where?
Those two.
Here?
Yeah, the N1 where I say G2.
So you're struggling here. Is that what you're saying?
I'm saying, well, here's my question. Let me phrase the question I was asking myself. Does the G2 actually have a compressive force on the N1 to hold it together? That was my question.
No.
And you're right. The answer is no.
See, I got this part down. I know that. Of course it doesn't. I mean, you can just use the same analogy as if it's G1, it was a sun or a planet or even us.
The G1 hit, here's my reason. Because the G1 I consider as kind of a basic particle at level 1. Basic particle.
It is the particle at level 1. There's just nothing like it, even in the nucleon, because it does so much.
In the nucleon, my opinion, because the G2 has to pass through the G1 and the N1. Right. The N1 is made up of, quote, one possibility, multiple G1s. Many G1s. Because that provides the space for the G2 to go through.
But the question is, yeah, the only thing I would say is, and we just don't know. I mean, how is it that, where you have G1s coming together and then you get them in orbit? Is it just, they're pretty stable, right? Yeah. So it's, it could very well be.
Our particle model doesn't preclude,
of course, yeah, we
two G1s going through space and G2 gravity putting them together. Our model doesn't preclude that.
Sure, but
that's hard to. Orbital, and depends on which way the orbits go. You have figure 2 and 3 down there.
So Dad's suggesting that there is no N1. It's just
No.
more G's.
No, it's a it's a large version of, the fact is, no, you're right. You're right. You could make the suggestion that way, and instead of being multiple G1s, it doesn't have to be a specific multiple of G1s. Just has to be big enough to be a central mass for an atom and be able to carry a G1 in orbit going speed c.
Mm.
See, when you have all those conditions, you end up with constraints as to of what it is because of the size of the G1 and the speed of the G1, the mass. Well, who knows? We really don't know. But the point there is, G1 is not a compressive force on the Earth any more than an asteroid hitting the Earth is a compressive force holding the Earth together. It's the same type of analogy.
Right.
Anyway,
I
so
gotcha.
there will be some words in there about a G3, but it'll be whether there's a picture or not, I don't know. But I usually bail out on the G3 because there's no evidence. No direct or indirect
Yeah, that
evidence.
one's harder. That's harder to sort of justify because,
But the model requires it.
model requires something to be in there. Yeah. Yeah. I mean, if you have things orbiting, that's the whole thing. I mean, it comes back to our classifications, our classifications from our website, which we have, the movement classifications. So if you have anything, according to our model, if you have anything that's a curving orbit or a not curving, but curving around something like the thing changes direction, like light will change its direction in a prism, then you have to have some type of gravitational field below that to be making that happen. So, and that's from the movement classifications page, which we have right here. And not only that, movement classification, we're going to be having a T-shirt pretty soon. Well, I don't know, pretty soon. I think I'm trying to order those, but let me see here. Sharing, stop sharing. I'm going to share again. We're going to show you the movement classification from our website. There it is. I can actually make it bigger, but then we get all this other stuff. I hate this with this resizing and stuff. But there's a classification of magnetic, gravitic, electric, and a new word, luminic. So we have that, and then we're going to be having a T-shirt just like that, because those are the 4 most important things of our model, which is basically what particles can do. They can cause a field, a gravitational field, a magnetic field is what people call it, electricity, which is just directional flow, and then light, which is waves of particles flowing in the same direction. So we've got that coming soon. Okay, anything else we want to discuss tonight?
Well, we had a list of some things. We wanted to talk about the applications. You mentioned applications the other day of TPM. I don't know. Was this flying cars?
Yeah. Well, the applications is what can people use with this model that they couldn't do before. So the idea is when people get a new model, the question is what can someone do? What could engineers or tinkerers do using the model that we couldn't do before? That's the question.
That's the question. Yeah.
And the idea is that if you have a new model, that new model should sort of inspire and should have implications in technologies. For instance, if G2 particles travel at c squared, we could send waves of G2 particles and send them out and detect them on a detector. We could then communicate to Mars in 1/4 of a second. That would be good because you could drive rovers around, and you could instead of having to write all this software, you could literally communicate almost instantaneously, practically, and be able to control those. So, what are the applications that
Well,
people
how
could think
about-
of?
How about
Gravity control.
predictions instead?
I don't know what you want to call it. Yeah, but I
Yeah.
mean, it's not predictions even. It's just like what are some of the technical what things could people do? Well, if you have first of all, right now there's nothing that goes faster than the speed of light, right? That's the standard model.
Yeah.
Well, we have a particle that goes faster than the speed of light. It has to. What's the evidence for it? It's what people call the electric field, not electric fields. It's the Coulomb force. It's the Coulomb force.
Yeah, but
That's the G2 field,
yeah,
right?
Yeah.
So that goes faster than the speed of light. What is the Coulomb force? What do they call it?
Well, that's the the force, the electric force that pushes two charged particles.
Yeah,
together.
electric force. So the electric force for pushing charged particles together is made up of a field that goes faster than the speed of c. And if it goes faster than the speed of c, then like I said, people would have to find out, can we somehow make a gadget that would send those out? And if you could, then can you detect them? And of course they're
Well, the electron gun, which I was really working on today, you can adjust the voltage and change the speed of the G1 particle. Now, I disagree with their explanation, and for a while there I almost disagreed with ours, but I believe it worked out. But the point is, you can vary the way you vary the speed of the G1 is with the electric field. But what they don't know is the electric field is not, but they think it moves at speed c.
right.
Now, the problem there is, how do you move a particle that's already moving at speed c with another particle that's moving at speed c? You can't do it, at least not gravitationally. You can hit it and bounce it around, but you can't do anything. You can't move it in a curve, and yet they do. They measure the electron mass by adjusting the voltage to an electron gun, adjusting the current to some Helmholtz coils to make it go in a circle, and they go through all that. There's a video on that measuring the electron mass that I've made. But they're actually controlling the speed of and they think they're controlling it with an electrical field that's only going at speed c. So they're believing a little bit of magic. Well,
I know. Yeah.
because in a particle model, that electric field is replaced by G2 gravity, and G2 gravity is moving extremely fast.
Right.
And can change the flow of an electron beam gravitationally. So they're doing it, they're using it, but the effect is they're only changing the speed of light or of the electron, either way you want it, whatever which one you want, because you do the same thing with well, I was thinking of bending of light around the stars, but so the question is, where does that get you? Does that help you do anything to know that that you have now control? You actually have control of this electric field because you change the voltage in the battery source. When you increase it, they claim that you increase speed, and you do. They just explain it wrong. But
Well, they don't have a model, so what are they explaining?
but so they are using high speed G2 particles to do that experiment and ultimately measure the mass of the electron, and unfortunately they do it in kilograms, which is also incorrect according to the particle model. So there's something there. Well, if we're able to control the speed of an electron with that, and we're using a force that's faster than the speed of light,
I'm not saying.
give me the next step. Start brainstorming the next step, and right now, so maybe the clue is the electric field is to move forward. How many different ways? We use the gravitational field to control the magnetic field. Same thing, and the magnetic field is a G1 flow around and through the magnet, and it's the G2 gravity that is controlling the direction around and through, just like an orbit. So, we have this electric field or G2 force that is very fast.
Say hello to Jacques. Remember him from Brazil?
Okay, let me say this. Why can't you continue to use that electric force to make the G1 go faster than the speed of light?
Yeah, but the question is how much faster, right? And maybe
Probably,
just
but
by very little.
I don't care if you can go a little bit faster.
But what are you accelerating to that? Wait, hold on. Jacques Cardema, the guy who was in Brazil, is watching us right now. Hello, Jacques.
Oh.
You don't remember Jacques who took us on the climb?
Oh yeah, the Jacques. Yeah, I remember. I didn't remember the last name, but I do remember Jacques.
Cardema,
yes.
yeah.
Very, very nice.
He just stumbled in. He's probably thinking, "What the heck are they even talking about?" So, but anyways, yeah. I mean, but you're talking about G1 accelerating G1s faster than the speed of light.
Well, I'm just thinking right out loud. Okay, I'm saying you got an electric field that is going faster than the speed of light. You ought to be able to push the G1 faster. Why doesn't it go faster? The atoms won't. The particles. Not the particle. Let me say this right if I can. Anything that is controlled by G1 gravity will not move faster than the speed of light.
Right.
That
Yeah.
I know. So when you talk, remember the picture we had, when you talk about the molecules that are big enough that G1 gravity is effective on it. It's not effective on an atom. Why can't you move an atom faster than the speed of light? Because there's no G1 gravity that's going to slow it down. No G1 particle field is going to slow it down. Why can't you move an atom, the hydrogen atom, or even the hydrogen gas? Why can't you move it faster than light? Because there's no G1 drag.
Yep. Farouk's here. Hello.
I rest my case.
Hello, Farouk. How are you? He says, I want to talk. Well, I wonder if I can get him in here. I don't even know. Let's see. Oh, yeah, you can invite. You can. So here's a link. There's a link, Farouk. You can come into our waiting room. We can put you on. You don't get on the air right away, but you don't even have to have video. You can just have audio. So we are here talking about we're having a meeting this weekend about the book. We are going to be doing a lot on the graphics. Trying to get more graphics done. And then we're going to have, of course, once we get all the graphics done, we're going to be very close, print out a version of the book, and then go through it once again, have people looking at it that are our editors. And then once it's done, then we can launch it. We're going to have a special version of the book where you can buy it ahead of time, pay for it ahead of time, get a t-shirt and a book, and signing it with a special note, like the crazy people who think they can tell you everything in the universe. But regardless, we are continuing to work on the book, and that's why we have some of our conversations online here for prosperity. So those who are interested in the model can know where we are. So anyways, I sent him, he wants to talk, maybe he wants to talk offline, but regardless, I think that's it for today, huh? I think so.
Yeah.
40 minutes into it, so. Alrighty. So if there are no questions, any questions, Farouk, that you may have, It sounds like we want to have a conversation with him. That sounds like something we can do. If you are interested, also, I will be tonight. I'll be going live, YouTube, at 9:30 Eastern time. Oh, there's Farouk. There he is. My goodness, he is here. Oh my
Hey,
goodness, there he is.
hey,
So,
hello.
well, hold on.
What do we
Hold on. We see him, sir. I'm going to bring him up. I'm going to see if he can. Oh, we've got to get. Oh, this is not easy. Let me see if I can do this. Hold on, Farouk. Get uh, we're going to get a, microphone, us to hear you. So just give us a second here. It's going to take me a little bit of time because we have two people, and how do I get two people? I know how to do it. So hold on. Just give me a second here. Um, Bluetooth. Get the Bluetooth, and then I'm going to. You're gonna have to put one in your ear, and I'll put one in mine, so that would actually work out. David is paired. Let me get it unpaired with my phone. Again, I'm just getting it so we can hear here. There we go. And let's see if I can connect. If I can connect to that, I can. There it is. And let's see the microphone audio. Mic. Oh, we have the mic, but the speaker is that, and I need to change it to iPod Pro. Let me test it. It is. We are there. So I'm going to have you put this one in your ear. It's going to be on this ear, Dad.
Good,
Put it all the way in there.
I never did one of these. How do you do this?
Okay, just put it in there. All right, we're going to bring Farouk in here. Let's see if he's there. Hey, Farouk.
Hey,
Hello, how are you doing? Nice to meet
Hey,
you.
I'm going to move. Yes, move over here closer so we can see you here, and I'll move this here. How are you?
I'm fine, thank you. How are you doing?
Fair, very good. We've got a setup here. I didn't expect that. I got one ear here, and my dad's got the other ear. Can you hear him, Dad?
yeah, I can hear him.
Okay. So first of all, thank you for all coming by and watching what we're doing. You are interested in science, but obviously are not a person who thinks about the standard model is necessarily correct. So how did you come about to be sort of a dissident scientist, a person who's trying to think of better ways that the universe could be described? How did you get there?
First of all, I want to thank you, both of you, for all what you are doing. I'm from Morocco, by the way.
Oh,
It's in North
Morocco!
Africa. Yes,
I went to Tetuan. You know Tetuan?
yes, I know Tetouan.
It was
Yes,
very beautiful, but I won't tell you how long ago because you weren't probably not born. But it
I'm
was
32
19.
years old.
How 33? 53?
30,
33.
32.
Right. I went there in
No, no, no.
1985.
I am 32 years old.
Okay, 32. Okay.
Yes.
Got you. Okay, but it's very beautiful there. Very beautiful. So how did you get involved in dissident science, meaning different ideas? Why did you come to those ideas?
First of all, I wasn't searching about physics for a long time. I had some existential questions, and I discovered your channel in. It was a hazard, so it wasn't. It was a coincidence. I typed in YouTube "dissident science" just like
Right.
that.
Right.
But
Wow.
before that, I was watching Distinti and Lori Gardi. So I was
Oh, Lori
interested.
Gadi. Okay.
Yes, I had a lot of question about science, and I try to educate myself here in Morocco. For unfortunately, the standard of education in Morocco is not like the United States.
Hmm.
I was very interested in science childhood, but I didn't have the opportunity to learn the
Hmm.
scientific method or philosophy.
Right.
But
Right.
I'm very lucky to discover your work and everything else with work hard and the others.
Oh yeah,
Yes.
there's quite amazing work. I mean, even our
Yeah.
model is standing on the shoulders of a couple people. Denu's work, Borchert's work. You know, my father's his model for light, which I think is really great. Now, you know, Laurie Gardee and Yonel Denou are now working together on an ether model. You know that?
Yes, I know.
Yes.
I know what they are doing. I saw a preview of a video of Ether. Okay, I saw that.
Yes. Okay.
Mm.
So, are you an ether person, or you don't have a preference?
I don't have a preference. I'm intrigued.
Intrigued.
Yes.
That's good.
That's very good. You're like my father. He and I worked together for many years, and we even made it. I made the documentary Einstein Wrong, and we went through the whole documentary, and he didn't. I asked him, "Do you think Einstein's wrong?" He says, "I don't know." And he was in the movie called Einstein Wrong. But eventually he spent the time to look at Einstein's work and came to the conclusion, yes, he's wrong. It doesn't work. So it's always good to keep an open mind. I know my next video that I've already scripted for the Dissident Science channel is about ether itself. And I think one of the problems with ether is people don't think there is any other alternative to ether. And then I think that's been one of the problems is they think that's the only possible physicality for light, and it's not. I mean, my father's got a very good example. So that tends to get in a lot of people's way. You hear things like ether is has been proven, or ether or whatever. So I think it's good to keep an open mind about, both possibilities, because ether is one possibility. My father's model for light is another possibility. And I think ether has a lot of obstacles, in my opinion. I never got that real big feeling with ether the way I did when I saw my dad's light. I knew ether for 10, 20 years, well, probably 20 years. But then when my dad came up with his version of what light could be, I went like, oh my gosh, this is really good. It clicked with me at least, it was something, so.
So, do you have any questions? You wanted to come and talk, and I know you said you wanted to say thank you, and you did that.
Yes, yes, yes. You don't realize how much change you bring into my life, because
Oh,
because with the whole creationism and the beginning and the end,
right.
this is all that I knew in my life. Okay,
Oh, okay.
so the idea of infinity, when I understood that was like the enlightenment.
Right, yeah. Infinity,
So
yeah.
yes, yes, yes. It's something I am convinced. By the way, about the idea of infinity, I'm convinced, but I'm not convinced about your particular model or the ether. I'm intrigued.
Well,
Okay.
that's very good. That's very good. That's very good. I think that's what happened to me. It was probably about 12, 13 years ago. No, it wasn't even
Uh,
that long. I read the book Universal Cycle Theory by Borchert, and I understood
okay.
his infinity, and I
Mm,
just went nuts. It was like a big explosion of my brain. I thought, wow, this
mm.
is totally right, and it makes total sense. So yeah, we had that, and I had that same thing happen with Yonel Deneu's underwater experiments. That
I
blew
saw
my
that. Yes.
mind. And but ether never blew my mind. I know about it, but the problem with ether is I've been around it a lot, and I know a lot of the problems with ether. And one of the problems with ether is the idea that how do you get a laser with ether, right? You can't focus sound, for instance, in a straight line to go all the way to the moon and not spread out. So there's a lot of problems in an ether model that people today aren't addressing. I ask them these things and they're too excited. That's all right. I don't know. When know the answer there. And also the same problem. I think that it's interesting to see Laurie Gardee and Yonel Denou trying to make ether stay in a wire, right? Because it's a wave. A wave, you make a wave and the wave goes in all directions if it's an ether, right? Well, how do you make a wave travel through a wire? Because that's the way etherists would say. We don't have a problem because we have particles. Particles can easily go through there. There's no problem. We can simulate, we can make it go in all directions and make it like light is, or we can make a laser like that. But ether has that problem. And if you look at latest work with Lori Gardi and Yonel Danu, to make ether work in a wire, they've had to invent another element. They've had to, like, sort of fix it a little bit to make that, traveling in a wire work. And I think that's one of the reasons, I've been around ether. It just never grabbed me the same way as infinity grabbed me. It didn't grab me the same as Yonel Danu grabbed me. And it didn't grab me the way my father's light model worked. When I saw that, my head exploded in the same way. And that's one of the because again, ether has been around for almost 300 years, more than 300 years. Why hasn't it been solved, right? I mean, it's been around. And the reason it hasn't is because it's got elastic problems. It's hard for me to understand that the light coming from 10 billion miles away came by this hitting this particle, this hitting this particle, this hitting, collisions all the way. And it's got to travel 10 billion years in 10 billion light years in distance. And those are some of the reasons I am not an etherist, because there's just too many problems that come with it, even like electricity. And that's one of the things that Lori Gardi and Yonel Danu are trying to do. Now, if they're successful, I don't know, but they've had to already invent something for it to work. And to me, that's one of the reasons I'm not really an etherist, because it doesn't. There's too many things that don't work with an ether. And I think the problem with the ether community now is it's so big and there's no other alternatives, right? Well, that's the only thing we have. It's a light, is a wave, so it must be a wave through a medium. It must act like water, sound waves. But now that we have another model, which my father came up with, now we can say, no, ether isn't the only answer. And what of the two answers for a light, which one is simpler? Which one works better? And that's where we're at right now. And it's fun because, who's going to win? It doesn't mean that either one is right, but we're looking and working on the same problems.
I just want to say something. You talk about a lot of books in your Dissident Science channel. I want to thank you for this because all my questions are being answered. When I took courses in high school and later after physics and mathematics, it was all blurred. It's like
Right.
it was shrouded with the mists, or
Yes.
I couldn't know the beginning or the end of anything. Okay, and plus in Morocco, we don't. There's no experiment done in high school. For instance, in physics, only two experiments. We've done only two experiments. One with the rod and when the friction electrostatics, and the second one it failed. It didn't even work when the teacher tried to do it. It's when you turn a discs and you're supposed to have sparks, okay,
Right.
from two rods. This is the
Electrostatic.
only this is the only experiment that I witnessed in Morocco. So I'm thankful for the internet and the simulators and MATLAB and everything. Even if I can't do experiments, even if I didn't do experiments in high school, I can level up my knowledge and with the simulators and
Yeah,
that's it.
one of the things, the reason we're working on a model and other people are working on a model like Lori Gardi and Yonel Danu, the reason we're doing this is because we are tired after over 300 years of not being told what things are. What we have are lots of equations and lots of mathematics that can predict the movements, that can tell us where this is going to be, where a spaceship is going to be, how light is going to work, but we're not told what light is. We're not told what gravity is. We're not told what electricity is. We don't told any of that.
I want to interrupt you. I just want to say that you have no idea, because when I'm looking to when I'm listening to what you're saying and what you're presenting, the books of electricity, the Torres book, what's the name? Electricity. I have here the book. well, the books of Burckhardt and the
Yeah.
nature of negative numbers and absolute space, time, and motion, and the other book, Andre Koch Torres Assis,
Yeah.
the
Andre
experimental.
Assis. Yeah.
Yes, yes.
He's a good friend.
You're given the people the basics. You know the true basic of
Sure.
physics.
Sure.
How to start from scratch. This is amazing.
Yeah.
You
Yeah.
have no idea, especially for someone who is not from a scientific country. Okay,
See.
I wish really that all Moroccans could watch your channel and understand English. Okay, that will be amazing. Really,
Yeah. I think. Yeah.
thank you,
Yeah. Yeah. Oh no.
thank you
No.
very
Yeah.
much.
But it's
You
not
have
just
no
us.
idea.
But it's not just us, right? And I think the other thing is too for is that even when you look at Andreas Cease or you even
Yes,
he talks about very simple things which are very good to look at. But
yes,
again,
yes,
what we're trying to do is go one step further than even Assis and say, not only is this happening in their very basic, which I love Andre's work, but this is
yes,
what is really the physics of what's going on. Because what we have is we have one of the biggest problems that my father and I see and other people see, and I
yeah,
think Laurie Gardy and Yanel Denou also see, is that we talk about charge, positive and negative, and we talk about how they attract, and we never tell anybody what that means. We never say how that happens, but we have charged particles that are negative moving, and it causes a field. And does the field cause the charge, or is the charge causing the field? All of that is such a futile attempt. It's very frustrating because in the end, if you don't have a model, you're not going to get anywhere. You're going to talk about it as this, you're going to talk about it as that. But when you look at our model and we look at the static electricity, electrostatics, you look at electricity, our model tells you what it is and why it happens. There is no charge. There is no positive or negative. We know why things come together. Those are the kinds, that's why we think the model is important. Whether it's right or wrong, to me, it's not as important as that it's trying to do something which other people aren't doing, and that is to give physics of what's happening. So when someone
I
comes to
prefer,
on this,
yes,
yeah, and
I prefer
that's
your
what we're at.
answers. I prefer your models than what I've been taught. For instance, holes and electrons.
Yeah,
What is that? Holes, and also magnetic waves and
right.
magnetic fields.
Fields, right.
I asked that question many times to many professors.
They
Even
don't
one
know.
time, I said to one of them, "What is this made?" And that I asked a professor from a French university. Okay, he
Hmm.
came to Morocco, and I asked him, "What is it? Is this made of ghost or butter?" And he gave me answer which is gibberish. He tried to appear smart, but
Yeah,
I knew that he didn't know.
yeah. He doesn't know. It's amazing to me how if you go to a person on the street and they call it the standard model that we have now, standard and model. It's not a model at all. It's zero model.
Mathematics.
If you go to Wikipedia and you look up look up a quark. A quark is supposedly a subatomic particle. We say yes, it's right. If you look at the picture, all it is circles. There's no physicality anywhere. And then they give them, like Alexander Unziker says, they give them arbitrary attributes. Oh, this one's called blue color. This one's called strangeness. This one's called charge. And they put them on, and then they say that's what, it doesn't say anything. It doesn't tell us. And that's why I think what we're doing, right or wrong, when someone gets a book and they're going to go, oh, I don't care if these guys are right or wrong, but it's something. It's the first time someone even gave me an answer to that.
Yes, yes,
And that is why I think this book is going to be very popular. Not because, oh, we have some fancy idea. It's because people can go, hey, whatever it's right or wrong, I get that. And I can imagine that. And I can even see how that explains things. And then after that point, at least we'll get over that problem of that mathematics is what we get. Your professor's going to tell you math. He's going to say, well, we have an equation for this, and this moves this way. You're going to say, well, why does it move, and what's moving? And he goes, and then you hear gibberish. bad answers. Oh, it's funny descriptions that mean nothing.
It's
That mean
frustrating.
nothing.
It's really frustrating.
Farouk, if
Yes.
having listened to Dave and some of my talks,
Hmm.
I find for myself that I can visualize this, what's happening so much easier with this model.
Yeah.
Do you have the same experience? Did you?
Yes, yes, especially with the massage. Yes, the pushing gravity.
Hmm.
You know, I am talking about your work to my friends and members of my family, and one of my uncle. When I told them about the pushing gravity, he said, "Wow, this is it's
And
blew
it's
his mind."
I know, and that's almost 400 years old. That's 330 years old. That idea, right? Pushing
Yes.
gravity has been around for since Newton. But I think what's interesting is, and the other thing I think about the model that's to me is so amazing, is because they're that it's a progression. It uses Newton, it uses Lesage and pushing gravity, it uses Borchert's infinity, it uses Yonel Deneu's discovery of moving particles in circles that cause what looks like attraction and repulsion. And
Hmm.
you can use all four of those. And my dad, the last one is light. Light isn't a wave in a medium. It's just
Yes.
a bunch of particles coming at you like, hitting you. That is a frequency. Boom, 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 boom. It's a frequency. And it's caused by particles coming and hitting you. When I saw that, to me, all of ether disappeared. I said, all the problems that you can't solve with the ether, like, Yonel Denu and Lori Gardi, they're trying to solve, how do I keep ether in a wire? You can't. You have to invent things to do that. But when I saw that, so what's amazing to me is this model is built on other people's work, right? It's built, taking these ideas, and then when my father came up with the last idea, and that was a better model, in my opinion, than ether, I said, this is it. And then everything changed. And once you see that, it's funny because there'll be people who are new to science who will see this model and think, oh, for 300 or 400 years, science has been doing this, right? No. Go to your professor. Ask any professor on planet Earth what magnetism is. What is it really? What is it? They don't know. And the public doesn't know this. The public thinks we know everything. We don't know even what light is, what gravity is, what magnetism, electricity.
So did your friend really accept the idea then?
Yeah, did he accept the pushing gravity?
It was my uncle and my brother and two of my friends. They were amazed. Okay, you know, many times I didn't sleep at night after watching Robert's videos. Okay.
Oh,
Is that good or bad?
I don't know. You can't sleep. I'm sorry.
Yes, yes, yes. You have no idea. Sorry for my rusted English, but I
Your
have
English
so
is very
much
good.
respect for what you are doing. So much. You helped me to find a purpose in my life. Okay,
Oh, that's
this is
Oh,
how
that's
much
very
I
good.
love science. This is how
No,
much
no,
I
no,
love
no,
science.
no. No, no, I understand.
I
And
hope
I
you
will,
understand the spirit.
no, I do. First of all, your
Mm.
English is very good. The only thing I know is shukran. That's the only thing I know. So,
Shukran.
but I also like Moroccan food. I like the bread. I like the vegetables. I'm a vegetarian, and there's a lot of great vegetarian Moroccan food. A lot of good
Yeah,
food. But what? But
I hope one day. Sorry, people always bring the Moroccan food. Okay, people from other parts of the world always they talk about Moroccan food. But what I want is someday people talking about Moroccan science
well, you
and
can.
Moroccan
You can
people.
be it.
oh,
You can be it. You
It's
can
what
be
I
it.
want. This is what I
And
want.
I will tell you, being honest, okay? I've been around people who have been outside the mainstream, outside of regular science, who are very good
Yes,
critical thinkers. I've been around for
yes,
30 years. And the people who see this, there is so much to do. We are at a time that's very exciting. My dad and I's
yes,
book
yes,
coming out with a model, the first model, in my opinion, of everything in the universe, physicality for everything. Right or wrong, it's the first. At that point, it's a new world. And those people who see it, like you have, you see it, it makes your mind like everybody who knows our model, they say the same thing to us. They go, I can't look at the universe the same anymore. I can't
Yes.
because before I saw nothing. No one, I saw nothing. I saw magnets. They came together, and no one told me what it is. Now I have something there, and so yes, in Brazil, for instance, my wife is Brazilian. There are like 5 or 6 Brazilian scientists who are good.
Yes.
Each, in fact, I think there's a few scientists in our database from Morocco. If you go to our organization DB, I think there are some names listed on Morocco. If you go to our website, I'll send you
Yes, yes,
that
yes.
information. You may find there are some dissident scientists, I think from Morocco. Not many, very few. But you are way ahead of them already. So,
Okay, Farouk, we added
Yes.
a new part in our book just recently. We're talking about the
Yes.
book. It's
Hmm.
a paragraph, a section on Hack 3.1, which is every Hack 3.0 is a big section that we've written that describes what we've done so far.
Hmm.
Hack 3.1 lists some very preliminary things of what we have yet to do.
right. We haven't, what we do is we take the rules of our model and we apply them to the universe. We've been doing that for 5 years. Now we've solved some problems, meaning we can describe things that no one else can describe, like dispersion,
Double slit.
white light going to a rainbow. We just
Mm.
finished that just a couple of weeks ago, the right model for that. It took us 5 years. But there are other things that we try to apply. Electronic circuits, my dad's doing. Reflection, refraction, gravity. We have a lot of things. But there are some things we don't have answers still because we can't apply it to the whole universe. So one of the things that people can do is to come up with the explanations using the model that we don't have explanations yet
But we
for.
haven't even tried.
Yeah, we haven't tried.
You
Mhm.
just can't get to everything. I at my age I have to pick and choose what I do. I can't just like so.
So anyways,
I'm
can
gonna be doing circuit experiments
so
to show that the current is not equal throughout the circuit.
yeah, our model is telling us things in even electronic circuits, that things that no one really has thought about, and my dad is measuring that. And he's an electrical engineer, and he's a really good one. He made a very good living in research, so it was very high level electric engineering. But the model we have is giving us better idea of how this works and tells us things that we didn't know before. And he measures them, and we're seeing that it's true that in the circuit you have a current or voltage, right?
Current.
Current. And that current isn't the same everywhere, but it's supposed to be. People think it is, but it's not.
Mm.
So
Amazing.
so it allows you to open up those ideas.
So
So.
you can do experiments, and if they work, you got supporting evidence. Doesn't prove it, but it's supporting evidence. I'm going to do an experiment to prove that G2 gravity is is cause of splitting current into two resistors, parallel resistors. I have a planned experiment for that. Haven't done it. It takes time.
There's a lot of work, Farouk, and I think it's the whole thing is that how do you say your first name in English? How do
Uh,
you pronounce your name? Is it Farouk, Farouk? How do you say it?
Farouk. Farouk.
Farouk, Farouk.
Farouk with qaf. It's an
Uh,
asymmetric letter. Qaf.
yes,
Farouk.
Farouk,
Qaf, qaf, qaf. Qaf.
Farouk. No, I know
It's
what
not
it is.
K. It's qaf.
I
Yes.
know. I got
But
it. I got
I-
it.
it's not
That's okay
important.
because I have a master's
Okay.
in linguistics. I have a
Okay.
master's in linguistics, so I
Uh,
like to learn how to pronounce them. So it's my
it doesn't matter. What matters
Farouk,
is the size. Okay.
Farouk. Okay, I got it. Okay, but what I would say to you is that what we can
Okay.
do is we can send you a book. We're
I will
going to
buy
give you
it.
the
I
lecture,
will buy it.
but
I will-
no, if you can we send it to you though? Because can you buy it online?
Yes, I will try. I will do
Okay,
it.
if not, we can send you a book by mail. Okay.
th- I value your work, what you are doing. You are my teachers, okay, both of you, and the others.
Yes,
Work hard.
yes.
Uh,
Danu.
no, I don't know the new. Okay, I know the
Danu,
experiment, but I
yeah.
never read a book. I've read the Ten
Oh, no, no,
Assumptions
no,
of
no. Yeah, he doesn't have a lot of work written.
and
No.
I have the book, the Infinite Universe Theory. Okay, I
Yes,
bought
yes,
that book,
that's
and
good.
I've
Great
got
book.
I've got the book. The nature of negative numbers and the absolute
Oh,
space
yeah.
time.
By
I've
oh,
got
yeah.
also.
Is it Peter Erickson's book?
Yeah.
Yes, I
Yeah,
have
that's
those books.
that's an amazing book.
Yes, I'm reading them.
Yeah,
Okay.
because one of the things we say is there are no negative numbers in the universe. There are no negative numbers. And so when we use equations, we go through and we make the square root of -1 because our math system's all screwed up. And there is never,
Yeah.
and that's one of the things my father talks about all the time is that, this idea, the negative numbers comes from our number system. And there are nothing negative in the universe. There is no such thing.
Excuse me. I am amazed. I'm intrigued. There are these books, okay? These amazing books, and we still have the curriculum,
Oh, I know.
which is in which is not in phase with what is actual, what is
Yes.
okay. You understand what I want to say?
Yes. Of course.
How
It's
can
very
all these?
frustrating. Here's how it
Yes,
works. Here's how it works. It's pretty easy to understand, actually. What happens is this: when you get
yes,
a new model of the universe that makes you look at the universe and gives people something they haven't had before, and it's easy to understand that a book like ours and like our model could be the thing that opens it up. Why? Because the people like yourself, who do you think? How come you, Farouk? Why do you see our model and Borkert's work and my father's work and other the Lesage's work? All those people. Why do you see it and the professors don't see it?
maybe they have big egos.
No, because they are being taught they have to teach what they teach. And
Yes,
so what happens is when the public gets a new model and someone gets it and they understand it, they will have to change because the public will change. They will be very interested and they'll all be talking about the model and how, oh, this is the first chance at somebody giving a model for magnetism and for light and for gravity. And the regular people who love science will take that like you and say, this is great, and work on it, and things will happen. And the university eventually is going to have to say, this, we have to look at this.
In fact, they're probably going to have to fight with their students first, because the students will be arguing with them
Yes.
if they're critical thinkers, and they'll have some ways to argue, whether it's ours or Laurie Gardy's, whatever it is. They'll have
yes.
arguments to put right back at them and make them start thinking. They're going to have trouble with the students.
Yeah, and I think that the other thing is too is what's going to happen is that eventually the older generation will have to simply die and go further. That's what always happens. The young generation will be working on it. They're going to say, "Oh, this is crazy. This is too simple. It can't be like this. That's the way it always is." And once that happens, then this will become the only thing that we need to.
The older generation.
And the only thing that we have to be careful with is that when we get these new ideas, that we do not keep. We always say, nothing is right. No model in theory is ever right. It's what I don't know if my father said it or if I said it, but we said this model is less wrong than the one before. And if you think it's the only and the best and we're done, no.
Karazani said he quoted it on the back of his book, Storm in Physics. He said there will never be a statement or equation invented by man that will ever be precise or correct or something like that, absolutely correct. never be, because you can't do it. It's too even with our simple model, it becomes too complex, like we were talking here with the copper things. But Dr. Karazani, that's where I got it from.
Yeah, it's a point to which where we have to get to a point where the general population who loves science, who are not getting the answer, and the good thing today is, Farouk, is that the generation today, even my generation, with all the lies that people are telling, all the things that people say is good for us. Oh, it's good to have billionaires and have one person own more than everybody else. That's not good. People now are saying, I don't believe everything they tell us. That when a science teacher tells us that this is so great, like relativity, it's so great, and then you ask them, well, what does it do? Well, I don't know, but the whole universe runs off of it. Well, give me an example. They can't. So the whole thing is now we're at a time where we have not only science, but many other things, politicians, happiness. People in the United States now are staying at home, and all they do is push money from this point to push money over here. That's their job. They're going, am I happy? Pushing money from one place to another? I want to do something in my life that means something to me. So we are at a point at which I think when our book comes out, people are going to say, hey, I'll try a different idea because the ones we have aren't working. So I think the climate of human beings today is at a changing place. Things are going to change for the better. So I'm really thinking that, and that's why when we are doing our book, we are talking we're not talking to professors, we're not talking to scientists who believe in the standard model. We're talking to people who love science, who want answers, and that's what's going to happen. Once science lovers, if millions of people like the particle model in the book comes out, then science will have to pay attention. And that's the way it always works. It works from the masses to the experts, and then eventually we get new experts like yourself. You say, I'm going to go to college now and I'm going to use the particle model, and I'm going to use an ether model, whatever model it is, and I'm going to change and make science go forward, and there's nothing they can do. They can't stop you. So well, anyways, I'm really amazed, Farouk. I want to congratulate you on your ability to understand things, your open-mindedness, how you can accept. You have exactly what Aristotle said, and that is what he said is the mark of an educated mind is for someone to accept an idea to entertain an idea. Oh, you have a particle model. I'm going to look at it and not judge it, but say, what is it? What are you telling me? And I will make up my mind. Most people, when they see it, if they already believe in something else, like an ether model, they go, I'm not going to look at it. And I think that's crazy, because I look at all of the models. One of the things that I am very different from other people who have their own models, I look at all of the models all the time, because there's good ideas in all of them.
My head is empty. I'm like a baby, okay? I'm open to everything.
Right, that's good.
That's the Buddhist mindset, okay?
Right, yes. It's very good. And I think that's what people need. And it's funny because if the people who criticize our model the most, the people who are the biggest critics of our model, right here, this guy and this guy, we're the ones. We are constantly, every day I'm thinking, oh, this can't be right. But the problem with our model is every time we try to break it, we find an answer. And to me, that's very exciting. It's very exciting. It's not answers everything. There's problems with it. But every time we ask the model, say, can we solve this problem that no one can solve? We find a solution. Sometimes it takes a week. Sometimes it takes 5 years. But that's what keeps us going, is because it continues to answer questions and give us ideas. And like you said, it gets in your mind, you can't stop. And when
Yes,
something is good,
Can't sleep.
yeah, you can't sleep. You don't know how many times
exactly.
he's
So
woken up,
excited.
I've woken up with ideas and thought, oh my gosh, here's something that's we have and we must. So that's one of the things, the reasons I am doing this with my father and you're here today is because I wanted to record these discussions. Because if we don't know, but if this model turns out to be something worth everybody to look at and that it could be very useful, I want to make sure we have our thoughts here so it gives other people ideas as well. And they can either say, no, Dave and Robert, Bob, this is all wrong. This is a better idea. Well, we want to record it so that people around the world can either say, help out, or move it in a new direction, or come up with their own ideas, right?
It'll either make us guilty or heroes.
Yeah, we're either going to be heroes or we're going to be zeros. But
We
it's
will
funny
be,
because to me it's not important for me personally. There's no ego. What I would love to say is that my father and I helped advance science. Now, if it turns out to be big, wow, that is super great. But it doesn't make anything, it doesn't do me anything to be famous, or I'm going to go and tell you, Farouk, what the truth is, because that gets you nowhere. And I think that's one of the differences. Some people have their new models. I know them. I know lots of them. I know people with at least 12 models, at least. And sometimes they get married to their models. They love their model. This is it. Everybody else is wrong. You can't do it like that. You can't do it like that.
truth cannot be expressed with words.
Yes. Yes. Okay. Do you have any other questions for, again, congratulations. I'm going to be coming on at one, in an hour time. I'm going to be doing my dissident science channel. That's a little different. It's not only the particle model, it's more of a bigger thing about talking about science in general. And so I'm going to be doing that. So we're going to go off the air here. But if there's any time you want to do a chat together, it would be great. I think the problem is when I do it at 9:30. Right now it's pretty late there, isn't it? What time is it where you are?
It's 1.5.
One in the morning, right? So what I'm
I was,
thinking.
look, I was about to sleep, and then I saw the live, and I couldn't stop from.
Okay, but
Okay.
what we can do is I can have a special session earlier for you, and we can come on and then talk. I think it would be really interesting. I think your attitude, I would like to do that because you are a very good example of how to approach science, how to look at science, and that is with the mind of a child. That's really why people who do move science, they have those kinds of minds. So I will try to make an effort for us to come at a time where you can come on, where it's not too late.
I
don't like to talk about myself. Okay, I'm not interested
no.
in myself,
Oh, I know.
but I have a heart of a scientist deep
Yes, you
down.
do. Yes.
Even if I'm living in an unscientific country, which I don't mind, because you know what? Because I have you, and the others, and the book, and the internet. This is our power.
Yes. Very much so. And the other thing
You
is
give,
too, absolutely.
you give me power. You give me power, and you opened a
Mind.
big door for
Right.
knowledge. Okay,
Right.
this is amazing. Anyone in the world can do this.
Right.
Okay.
Yes.
Yes. Okay. Thank you so much. And we're going to stop here. And
Yes.
I have a very good night's sleep. I will. It was wonderful to meet you. Congratulations. You are your science mind is very good, very good. I talk to you the same way I've talked to many famous people like Borkert. You could sit down with me and my dad and Borkert and all these people.
Please.
You would be fine to be able to talk
Yeah.
with these people. And that means we're all at the same place. So you are at the same place as all of us are.
Say thank you to Bocard. a
I
lot.
will.
Give
Yeah,
him a
yeah.
kiss from me.
Yeah.
Yes, I
Thank
will.
you.
Okay. All right. Good
Bye.
night.
Night, everybody.
Good night.
Goodbye.
Bye bye.
Bye.
Alrighty, folks, that was Farouk, and he's from Morocco. He has an amazing mind. He's been following our work, Laurie Gardy's work, Borkert's work. He is just like us. Borkert is, I keep telling him in my videos that he's one of the most important scientists of our time. I think our model has a lot to give the world. I think people are seeing it. And the ability to keep an open mind, like as Farouk says, as like a child is very important. And that's the way I've seen this, and I described it even 20 years ago, is that having a mind of a child, where a child will walk up to a, let's say there were 10 people, and 10 people had models of the universe, and they had those constructed and put it on a table. And we were at a place, a public place. If you take a young child who loves science, even if they're like 6, 7, 8, 9 years old, they're not going with all these preconceptions. They're going to the tables like, whoa, this is really cool. What is it? And then they go to the next one. Ooh, that's cool too. What is it? And having that mind of a child where you say, ooh, what is it? When someone makes a model, even if it's based on ether, which I don't believe is necessarily the right model, I still look at it with, and I really admire it because there's a lot of work being put into it. There's a lot of things that people are trying, and I always learn something from it. And who's to say they're not right and I'm wrong and they're right? So the idea is always to keep your mind open, look at all the things. Eventually, though, and I will say this, that's happened to my father and I, eventually certain people and certain concepts will hit you hard. Like to me, they were epiphanies, or they were, aha moments, eureka moments where, oh my gosh, that is amazing. And those amazing moments are ones you collect, and that becomes your science philosophy. And so the whole thing here is to try to teach and keep ourselves uh, in that mindset of a child and not leave that. And all the best scientists I've ever met in the world and talk with, and some very high level scientists, they all have that. They have this curiosity that never goes away, childlike curiosity, and that keeps them with an open mind and allows them to discover those aha moments, those eureka moments, those amazing moments that we all have. So thank you very much, Farouk. We will be talking many, many times, I'm sure, in the future. So take care, everybody. Thanks for listening in. We'll be doing updates on our book as much as we can. And I'll be on air in about an hour's time from when this is recorded on Dissident Science, where I talk more about general things in science and how we are going wrong and not looking at things we need to, and not looking at the truth like a child does. So if you're interested in, not only this one is about our model, our particular model of the universe, Dissident Science, we talk about all of science and the right attitudes and what's important, and things that we know are probably better truths out there than mainstream science. And I'm available for people to ask questions as well. But thank you very much. So say good night, Dad.
Good night, Dad.
See everybody later. Good night, Farouk. Sleep well, and we'll, I'm sure, talk again very soon.